Hello students, this is your physics teacher. Today we are going to start a topic called Lenz law. But first of all, let's do a quick revision about the Faraday's law of electromagnetic induction. So here it is, the Faraday first law of EMI. What does it say? Whenever there is a change in magnetic flux linked with the coil, current is induced and the induced current lasts as long as there is change in magnetic flux. So there must be a change in magnetic flux, and for that either it should be there should be a relative motion between them, or the area should increase, or the magnetic field should change for getting the change in the magnetic flux. And the second law just gives an idea about the measurement of the magnetic flux. It says that the induced EMF is proportional to the rate of change of flux with respect to time. That is, if the change is d phi and the change takes place for a time interval dt, then d phi by dt will be called the rate of change of flux, and the EMF will be proportional to this one, d phi by dt. So these are the first law and second law of the Faraday. But matter is that Faraday had not given an idea about the direction of the current, and it was given by the Lenz law. Okay, so let's start the Lenz law. The statement of the Lenz law is the direction of the induced EMF will be such that it will always oppose the cause of change in the flux. Okay, means that the condition due to which there is a change in magnetic flux, that condition will be tried, okay, to change, okay, by the induced current. Okay, so the direction of the induced current will be in such a way that it will oppose the cause. So how? Let us see. If the magnet is brought closer to this coil, in which direction the current will move? Okay, if I am being from this side, let us suppose if I am being from this side, then in that case the current will be induced in such a way that the phase which is in front of this north pole, it will create a north pole over here. That means if there will be a north pole over there, the current will be anti-clockwise. The current will be anti-clockwise. Clear? Only to oppose the change in flux, because if this magnet is brought closer to it, okay, and south pole is developed over here, in that case what will happen? This south pole and this north pole will attract each other, and the magnet will move with more rapidity towards the coil. And if there is more rapidness, there will be more change in flux, because the time interval, d phi by dt, if there will be acceleration, of course the dt time will be less, and E is inversely proportional to dt. So in that case the EMF will be more EMF means more power of the strength of the south pole, that we have assumed that, let us suppose south pole is developed over here. So if the south pole will be more will have the more strength, in that case south pole and north pole will attract with more force, and again it will move further with more rapidity. So we will find that without giving any extra energy to it, or without doing any extra work, the change in flux is continuously increasing, the rate of change of flux is continuously increasing. That gives the current, okay, without doing the equivalent amount of work done. Okay, so here a north pole will be developed in place of south pole, because north pole developed here will oppose this north pole, and for bringing it closer to the north pole we have to do some work, or the agent have to do some work, and that work will be converted into the electrical energy, equivalent electrical energy. So here we are finding that the statement Lenz law is in accordance with the law of conservation of energy. The same thing happens if it is brought away from the, let us suppose the magnet, it is brought away from the coil. What will happen? The face, okay, the face of the coil facing the north pole will have the south pole developed over here. Why? And for the south pole to develop, the current direction will be clockwise, because if that will not happen, in that case the north pole will be developed, north pole will repel each other, and due to this magnet will move away from the coil with more rapidity, because there is a force now, extra force. The agent is doing work and also the force is also doing work. So of course if there is a force, there will be more rapidity in the flux change, and if there will be more rapidity in the flux change, del phi by del t will be more, the EMF induced will be more, the south pole, sorry, here the north pole assumed, here the north pole assumed will also be having more strength, and that north pole and this north pole will now repel with more force, okay, and ultimately we will find that just we have given a push to the north or to this bar magnet, okay, and it is going away from the coil on its own without doing any work. The change in flux is occurring with more rapidity, and the induced current is induced over here. So this is not possible because energy is conserved. Here we are getting energy, electrical energy, at the cost of no energy consumption from our side. Energy cannot be created, it can only be converted from one form into another form. So here, to bring it away from the coil, to bring it this bar magnet away from the coil, the agent have to do work, because north pole and this south pole actually developed will attract, and to make it away from, the agent has to do some work, and this is Lenz law say, and the mathematical expression is that E is equal to minus d phi by dt. It is a single coil, but if it is a let us suppose consisting of n number of coil, in that case we will write like this: E is equal to minus n d phi by dt. Here variation sign, okay, if we have removed the variation sign and we got the equal sign, there will be a proportionality constant over here, but we have chosen the unit in such a way that the constant becomes unity, and so we haven't written it over here. So thank you for watching this video, hope you liked it, and you can share this video with your friend so that the other student will also get benefited from it. Thank you again.